Hi everybody. So this next section, the last section of chapter 5 is on 5.6, and this is about substitution and area between curves. Um, so we already looked at the substitution rule in the last section, um, but what we didn't look at is the substitution rule involving definite integrals, and this basically works the same as it did before. You just substitute the numbers into your integral when you're done doing it. There is a sort of a second way of doing this, and so you can either plug the x limits in, so in other words replace the u with everything in terms of x and then plug the numbers in that were the original limits, or you can actually change the limits of integration by plugging them into the function that you substituted for. And so I'll give you an example of this. Let's say, for example, that you wanted to evaluate this integral, right? So you could do some sort of substitution like u is equal to x cubed plus 5. Then to get the new limits in this case, what you would do is just plug the upper limit in for x in that expression, plug the 1 in for x, and you'll get 13 here and 6 here. And so when you transform the equation into u, right, instead of 1 and 2, you'll have 6 and 13, right? And if you do the substitution, right, you'll get du is equal to 3x squared, so you'll get du over 3 is equal to x squared dx, right? So in other words, just replace x squared dx, right? In other words, this, right, replace that with du over 3, right? And then you'll get u to the 7th. And then just evaluate that integral, right? So the antiderivative of u to the 7th, right, that'll be u to the 8 over 8. The 1/3 will come out. And then you can just plug in the 13 and 6, and that will give you your answer, right? Now, alternatively, what you could do is you could replace the u with the x like we did before, and then plug in the original limits of integration, the 2 and the 1, instead of the 13 and 6, right? You can do it either way, right? Either way you do it, you should get the same answer. Okay, so you can do it whichever way you prefer. I will typically do it the first way, where I just plug in because it's just easier than switching back to the original coordinates. But so for example, let's say you wanted to evaluate this integral, right? The substitution would be u is equal to x squared, right? So you get that du is equal to 2x dx. So you can just replace the x dx with du over 2. Sorry. I guess we had the 2x, the 2 in there too. Sorry, I forgot about that. So you can just replace the 2x dx with du, right, and then you'll have e to the u. Antiderivative of e to the u is just e to the u, so plug in your new limits of integration, right? Instead of the 2 and the 1, you plug in the 4 and the 1, right? Again, you get that by just putting in 2 in for u here, 2 in for x here, and 1 in for x there. And you get e to the 4th minus e to the 1st, which is about 51.88. Right? Or alternatively, you could replace the u with x squared and then plug in the original limits of integration, you get the same answer. Okay. One thing I want to mention is that if you have even limits of integration, you could basically just integrate from 0 to a, or I should say if you have an even function, not even limits of integration. If it's symmetric with respect to the y-axis, right, you could just evaluate from 0 to a and then just double it. Also, if the function is odd, and you're integrating from like a to negative a, right, you should get 0 there, right? Because remember, the area here will subtract off from the area here, right? So these areas will be negative. So theorem 8 says let f be continuous on some symmetric interval. If f is even, then the integral from negative a to a of f of x, like I said, is equal to 2 times that, and if f is odd, right, and it goes from a to negative a, right, you'll get 0. So this is just basically a restatement of what I had here. Now, as far as, so that's really all you have to do in terms of the substitution rule if you have a definite integral. Now, if you have two functions like this and you're trying to find the area between them, you might think that you have to do something weird right here because the area here would be negative. Well, it turns out that really all you have to do is just take the upper curve minus the lower curve and then just integrate that, at least in most cases. So if you have some function, so assuming that f and g are continuous anyway, and f of x is always greater than g of x on AB, then the area of the region between the curves f of x and g of x from a to b is basically you just subtract the two functions and integrate, right? And you could actually integrate them both separately if you wanted to. So I guess you might wonder why that's true, right? Why the area here isn't negative. Well, if you think about it, you're sort of subtracting the area for the g of x anyway, right? So that would be, if it's the area there is already negative, right, it would become positive. So let's look at an example here. Let's say we want to find the area between cosine of x and x squared plus 2 from 0 to 2, right? So what we're looking at then is trying to find this area, right? So one thing you might have to do is make sure that you pay attention to which curve is on the top and which one is on the bottom, because if you do this in the wrong order, you'll get the wrong answer, right? So since the x squared plus 2 is always on top, at least between 0 and 2, and cosine of x is always beneath it, right, you'd want to subtract them in this order. And then, again, if you can simplify this or whatever you can, but otherwise you can just take the integral of each thing separately, right? So the integral of x squared will be x cubed over 3. The integral of 2 will be 2x, and the antiderivative of cosine x will be sine of x. And again, that's between 0 and 2. We're not doing any substitution here, so just keep the limits the same. And then just plug in the 2 for all the x's, subtract what you get when you plug in 0 for all the x's, right? Remember, sine of 0 is 0. So you'll get 8/3 plus 4 minus sine of 2. If you combine these two fractions together, you'll get 20 over 3 minus sine of 2, and this will all be 0, right? So you'll get this if you want the exact answer. If you want to approximate it, right, that would be approximately the answer there with a decimal. Let's look at another example. So let's say we want to find the area between y is equal to negative x plus 3. That would be this line, right? It has a y-intercept of 3 and the slope is in negative 1. And the parabola x squared minus 9, right? That's just a parabola shifted down by 9. So we're trying to find this area. Now this one's a little bit trickier than the last one, right? The last one we did, you were basically given the interval here, right? You said you wanted to find the area between 0 and 2. Now for this one, I didn't give you the interval, right? So one thing you're going to have to determine then is these points of intersection, right? And remember, you can do that by basically setting the two equations equal to each other, right? They're both equal to y. So just set them equal to each other and solve. So figure out where 3 minus x is equal to x squared minus 9. That's basically asking at what x coordinates do they have the same height. Solve that equation. It's going to be quadratic, so move all the stuff over to one side. Either factor it, or if you can't, plug it into the quadratic formula. In this case, we're lucky we can factor it. And then those will be your limits of integration, right? So this will be negative 4, and this will be 3. And then just in this case, again, this function is always on top. This function is always on the bottom, so make sure you subtract things in the correct order. So you'll get 3 minus x squared minus 9. Again, you can simplify this into negative x squared minus x plus 12. Integrate that term by term. We'll give you this. And then we're not substituting or anything, so just stick in your original limits. Stick in the 3 and the negative 4. Just watch your plus or minus signs here. And if you work that out, right, I think that should give you 343 over 6, or 57.167. Okay, so just watch out. There might be some problems again where you'll have to figure out the limits of integration on your own. That's the main idea there. So let's say you want to find the area between 0 and 2 on this curve, right? So this is 1. So what I want you to do is find this area here. Now, one tricky thing about this is that you got to be careful of is this curve is not always on the top, right? So between, looks like maybe between 0 and 1, right? This curve, I guess that would be the x, the negative, or 2 minus x squared, right? So that's the graph of negative x squared shifted up by 2, is on the top between 0 and 1, and from 1 to 2, it looks like it's on the bottom, right? So that'll happen sometimes. So basically what you want to do is just break this up into 2 separate integrals and evaluate each one separately. Again, you might want to make sure that that's where they cross. I mean, it could just look like it. I guess I didn't really solve that in this case. So let me maybe do that, right? So you've got x squared is equal to 2 minus x squared. So if you solve that, right, you'll get 2x squared is equal to 2. Divide both sides by 2, and you'll get 1. So that means that x is equal to plus or minus 1, right? So plus 1 would be there, minus 1 would be there, but we're not concerned with that. Or you could plug into the quadratic formula or whatever you want there. So the upper limit, so we want to integrate between 0 and 1, but in that case we want the 2 minus x squared minus x squared, right? Because in that case the 2 minus x squared is on the top. And then between 1 and 2, we want to switch things, right? Because in this case the x squared is on the top minus 2 minus x squared, right? So just be careful of your the order that you do that in your plus or minus signs, and then just integrate like you would normally, right? So here you'll get 2x minus 2x cubed over 3, plug in the 1 and the 0. Here you'll get x cubed over 3 minus 2x, plug in the 2 and the 1. Evaluate that, and you should get 5/3. Here's another problem. So let's say you want to find the area, and I guess this should probably say beneath rather than between, or between the curves and the x-axis. So this one is a little bit different. I guess the 2 curves in this case, one isn't on top of the other one, but you'll notice that the function changes behavior at this point, right, which is also 1 again. Again, you can figure that out by solving, but I'm pretty sure it's 1 in this case. So basically what you want to do is find the area here, right, this would be A1, and then find the area here, which would be A2, and then just add them together, right? So in this case, you just want to integrate x squared. I guess you could subtract 0, right, because the bottom line is y is equal to 0, but there really isn't anything there, so you could just do x squared. And then this would be solving for y, right? You'd get 2 minus x, and then just integrate that from 1 to 2. And again, you might have to graph this. If I don't give you the curve, you might have to figure out where it crosses the x-axis and things like that. But if I give you a question like this and you're not sure what I'm asking, like on the homework or the exam, just ask about it, and I might give you a hint as to what it looks like if you can't draw it or something. Because you might need to visualize these things to figure out what the limits of integration are, or what you're doing there. And then just to work that out, I didn't really work this out in a lot of detail here, but if you integrate that, you'll get 5/6, right? I mean, this will just be x cubed over 3 evaluated at 1 and 0. This will be, what, 2x minus x squared. That evaluated at 1 and 2. So this is just going to be 1/3, right? Plug in 0, you'll get 0. Here you'll get, what, 4 minus 2 squared minus 2 times 1 minus 1 squared. So that will give you, what, 1/3 plus 4 minus 4 minus 2 minus 1. So that'll give you 1/3. Those will cancel. Minus 1. Oops, something's not right there. What did I do wrong there? Oh, this should be over 2, right? Sorry. So let's try that again. So that'll be 4. That'll just be 2. That'll be a half. So we'll get, what, 1/3 plus a half? Yes, that gives you 5/6, right? Because the 2's will cancel with a 4. There's another example. Now, one thing I want to mention is you can integrate with respect to y, especially if the curves are sort of going sideways like that, in which case you'll have to represent the function in terms of y. But it's always, whichever one is furthest away from the x-axis minus whichever one is closer to the y-axis. And again, the rectangles would look kind of like that. Maybe just to do an example, let's redo this one, but let's integrate with respect to y. So in this case, if you sort of turn it sideways, this would be the upper curve and this would be the lower curve, right? And you have to solve the equation for in terms of y, so you'll get x is equal to 2 minus y for the upper curve, and then for the bottom curve there, you'll get x is equal to the square root of y, right? It gets plus or minus, but we want to pick the positive one there. So basically what you want to do is take the upper curve, which is 2 minus y, minus the lower curve, which is the square root of y, and integrate that. And again, we're doing this, remember, we're going in the y direction, so we're doing this between 0 and whatever that point of intersection is, right? Well, this is 1, and that also has a height of 1. So you can get that by plugging into either function there. So just integrate between 1 and 0, and you'll get the same answer that we did before, right? Because again, it's not a different, it's just the area, so it should be the same thing no matter which way you do it. So if I give you a problem like this on the exam and I say find the area, you could just do it this way, or if you'd prefer, you could do it this way. You should get the same answer. If you have a piecewise continuous function like this, you would just integrate this a piece at a time. So you just find the area underneath this piece here, and then just find the area underneath that piece. Right. I guess we aren't going to talk about this. I think this is mentioned in one of the problems. This is what's known as Leibniz's rule. You might use this at some point in the future, so I just wanted to show you that, but I don't think we're going to use that a whole lot. So, okay, hope that makes sense. If you guys have questions, let me know.